pleasure to introduce Professor Rafael Vazquez-Duhalt. He's a professor at the National Autonomous University of Mexico. He's a leading researcher at the Biotechnology Research Institute in Cuernavaca, which is a beautiful little town about an hour outside Mexico City. Had the pleasure of visiting there a year ago. He's been working in the field of petroleum biotechnology broadly throughout his entire career, starting with his PhD research in the mid to late 1980s, where he received his PhD at the University of Geneva. Went on to do a postdoc at the University of Alberta. After that postdoc, in 1994, joined the faculty at UNAM. He's worked in petroleum biotechnology, but I think he's also going to talk to us about some of his other research interests in remediation of hydrocarbons and detoxification of pesticides and some other areas that are very closely related. So I'd like to welcome Professor Vazquez-Duhalt.
Thank you very much. Thank you very much for the kind invitation. I'm really glad to be here.
Could I ask you to turn your mic on?
Sorry.
That's
yeah. Okay. Yes. Well, before start, I would like just to show you a picture of a piece of art of any carrying glass. It's an artist from San Francisco. Actually, I think she was not born in San Francisco, but she is living here. I like his paints, and I would like to show you and share with you this magnificent piece of art. Well, I would like to start with the most important slide. And this, all the people involved in the work, and several students, also faculty members and technicians, and some international collaborations. And they do most of the work that I will show you today. Well, 20th and 21st century we will know in history as the petroleum-based society. And probably in the future textbook, we will find pictures like this, describing our time. Two main problems, energy and environment. If the humankind wants to stay in this planet, should resolve these two problems, energy and environmental. Well, now we are in the production peak of oil. We know that. And there are several estimations how many oil is still to be harvested. I will show you some of one. This is the optimistic point, 3 trillion barrels. That means 3 times more than all the oil that has been already harvested. But the most conservative estimation are 1 trillion barrels, 1.7 barrels. That means still there is an equivalent amount of oil to be harvested than the oil that has been already harvested. As you can see here, there is 2 different profiles. If we continue producing oil with the technology, the known technology, or if we are able to introduce new technology in order to use and produce the heavy oils and non-conventional oils. And the difference will be quite important. If we use the same technology, probably at the end of this century, we will not have oil. And if we are able to use new technology, probably we will have oil for the next century. The question is, we will still refining this remaining oil as we do today, mainly based on distillation, or we will be able to introduce new technologies, membrane catalysis, gel permeation, and biotechnology. In order to produce clean fuels, we know that it's necessary to decrease the sulfur content and nitrogen content because we have the acid rain problem, and the solution is desulfurization. Also, we need to reduce the aromatic content in the fossil fuels, and the problem is carcinogenesis. And the possible solution is the aromatic transformation. And finally, in order to use heavy oils, it's necessary to remove heavy metals present in the oils because they cause problems in the refinery. And we need to do the asphaltene cracking. Before I start with the asphaltene biotransformation, I would like to give you an overview of the potential application of biocatalysis or enzymes in the oil industry. We will start with the sulfur content problem. As you know, this is the pH average map, and you can see red is low pH, blue is high pH, and you can see, well, it's a problem, the acid rain is a problem of the north hemisphere. Here you are contributing significantly, and this is a problem. In order to reduce the impact of the sulfur content in fuels, it's necessary to desulfurize the oil. Biodesulfurization, well, we know that now regulatory standards are important. Also, the decline of the easy accessible sources of conventional crude, and the high cost of physicochemical process in order to eliminate the sulfur, such as hydrodesulfurization. Most of the oil now should be desulfurized. Well, what is the impact of this desulfurization? You can see in Europe, this is the emission of sulfur, nitrogen oxides, and you can see after the regulation was set up, there is a dramatic decrease in the emissions. That means regulation works in order to make cleaner fuels. Well, long ago, 25 years ago, John Kilbane from the Institute of Gas Technology isolated a bacteria able to remove sulfur from the organosulfur compounds specifically. They elucidate all the system, the enzymatic system involved in order to remove these sulfur atoms. And they characterize all the enzymatic steps, as you can see here. And after 20 years' work, they were able to reduce the desulfurization time significantly. You can see this is the time using the soil isolate. And after several, well, obviously grow optimization, but also gene manipulation, they were able to reduce significantly the desulfurization time. However, this process is a metabolic process which is not possible to use in the oil industry because it needs low temperature and a lot of water. In fact, it just arrived up to a pilot plant and they stopped to do. We were proposing an enzymatic system in order to desulfurize the oil. Why enzymatic system? Well, because enzymes are able to work in a very low water content. Also, they are able to work at high temperature. The enzymes are active even if the system is toxic. The only advantage to use metabolic procedure is that the enzyme is self-producing. That means microbes grow and they are producing their own catalytic system. And in the case of enzymes, the lifetime of the process depends on the stability of the enzyme. That's the only disadvantage. But enzymatic process have all these advantages. For a time, we were exploring the possibility to use peroxidases and hemoproteins in order to transform organosulfur compounds. chloroperoxidase from Caldariomyces fumago, ligninase from several white rod fungi, cytochrome C, which is not an enzyme, but is a heme protein that in presence of hydrogen peroxide is able to act as a peroxidase, and hemoglobin 2. The products, well, we can see, and chloroperoxidase, this the most active peroxidase known so far. This is the structure. You can see here the heme group, which is the active site. It's an iron porphyrin group. And this is the catalytic cycle of chloroperoxidase. From the native state, in the presence of a molecule of hydrogen peroxide, in a 2-electron oxidation, they form the compound 1 that subtract an electron from a substrate to go to the compound 2, and then another molecule of substrate is oxidized to come back to the native state. Chloroperoxidase show also significant catalase activity. That means it's able to disrupt the hydrogen peroxide molecule, and in the presence of halogen ions is able to halogenate some substrates. It's a very versatile protein. Well, this is a list of organosulfur compounds and the specific activity using chloroperoxidase. As you can see, all of them are substrate for the chloroperoxidase. All of them are oxidized by the chloroperoxidase. We have tested probably 50 different organosulfur compounds, and all of them are substrate for chloroperoxidase. This is the products. It is a mass spectrum. This is the oxidation products from the dibenzothiophenone, the sulfoxide, and the sulfone. That are the main products. In all the other cases, also we got sulfoxide and sulfone as product of chloroperoxidase oxidation. And here is a diesel. Is a gas chromatogram from a diesel using a FID, a general detector, and using an FPD detector specific for sulfur. This is before the enzymatic treatment, and you can see the profile of the general detector follows also the profile of the sulfur compound. That's classic for a petroleum distillate. After the enzymatic treatment, we can see that the hydrocarbons are not modified. However, the sulfur compound, almost all of them are oxidized, and the boiling point has been increased. As you can see, the profile has shifted for longer retention times. If we do a microdistillation of these, we got this. This is the before, this is the control, this is the distillation profile using the general detector, is for obviously for hydrocarbon detector, and this for sulfur compounds. As you can see, before the control, before the enzymatic treatment, we got, they follow the same profile. After CPO treatment, after chloroperoxidase treatment, we got this shoulder that is mainly due by the oxidation of sulfur compounds. That means in one enzymatic step, we are able to increase the boiling point of exclusively of the sulfur compounds, and also the sulfur compounds become more polar. That means it's possible to make extraction in a liquid extraction system, or as we do in a distillation system in oil. This is the diesel fuel before. This is a distillation with a final distillation point 30 degrees lower. As you can see, without enzymatic treatment, we got almost the same sulfur compound, the same sulfur content in the fuel. And after enzymatic distillation, we got a significant reduction of the sulfur compounds. That means we were able to eliminate sulfur compounds of from the diesel fuel. That means it's a biodesulfurization enzymatically mediated. Well, we got a patent of this. It's a biochemical process for biodesulfurization. And how we imagine the process is very simple, because we need a reactor packet with immobilized enzyme, and we add few concentration of hydrogen peroxide. We are talking micromolar concentration of hydrogen peroxide, and then we can got oxidized sulfur compounds that could be separated by distillation, absorption, or another physicochemical process. This process is low pressure, low temperature, but could be high temperature, because enzymes are able to work temperatures higher than 100 degrees Celsius. And also, we believe that it's possible to have a process in which it's not necessary to add water into petroleum. That's important. Well, what's the problem? Why this process has been not scaled up? Well, chloroperoxidase, in the best of the situation, is able to transform 1 million of substrate molecule per molecule of enzyme. And if we make estimation, we need 1 gram of enzyme to desulfurize 1.4 tons of fuel. Since high or low is almost is very low in terms of economics. In our hands, using an organosulfur compound, it's a model thianthrene, we were able to oxidize 500,000 of molecule per molecule of enzyme. Still, we need 1 gram of enzyme to desulfurize 0.8 tons of fuel. In order to make this process economically attractive, it's necessary to improve the stability of this enzyme at least 100 times in order to have 1 gram per 81 tons. That's in order. And we are working, I will show you later, on this problem. Well, another problem of fuels is the aromatic content. Here in California, soon there will be legislation concerning the aromatic content in gasoline. And well, this is the polycyclic aromatic hydrocarbons, PAH for short. And what's the problem of these compounds? Well, they could be activated by a system, for instance, cytochrome P450 in tissues is a oxidation in 2 electrons to form this diol epoxide, or the pH could be activated by 1 electron for UV radiation, and both of these intermediates are able to form adducts with the DNA. This is the beginning of the mutation. This is the beginning of the cancer. It's for this reason these compounds are carcinogenic. Well, you know probably better than me the lignin structure. It's the most abundant aromatic polymer on Earth. And nature has a system in order to break down this molecule, mainly white rot fungi, which they have a battery of enzymes, lignin peroxidase, manganese peroxidase, versatile peroxidase, and cytochrome P450. These 4 are heme proteins, and lacase, which is a copper protein. But all of them are able to produce free radical. The nature is able to break lignin structure, making free radical mediators, and in order to go inside the wood structure and break down this system. And these fungi are responsible for the carbon recyclation of this lignin. This is good. Our enzymes non-specific are quite, and it's good for us. And also, well, they have system to produce hydrogen peroxide, which is needed for the lignin, for peroxidase activity. Well, all of these enzymes are also able to oxidize pHs. And the main, in the presence of hydrogen peroxide, I told you the concentration of hydrogen peroxide could be in the micromolar range. It's very low. Here is pyrene, one of the pHs, and the different enzymes, all hemoproteins. Chloroperoxidase, lignin peroxidase. This is a yeast cytochrome, hemoglobin, cytochrome C from Vibrio, is an anaerobic bacteria, and horse cytochrome for horseradish peroxidase. And as you can see, chloroperoxidase is the faster peroxidase in the oxidation of pyrene. It's order of magnitude more active than lignin peroxidase. These are the products. It's mass spectrum. It's mainly quinones and dions. And why is it important to make this oxidation? The question is, the products of the enzymatic transformation are more or less toxic? And here I'll show you, this is the minimal mutagenic concentration in human cells. This cyclopentapyrene is 1.8 nanogram per mil. It's a powerful carcinogenic agent. After one enzymatic transformation, the mutagenic capacity has been reduced order of magnitude, 3 orders of magnitude. In some cases, the mutagenic capacity of the compound has been disappeared, at least against these human cells. It's the case of benzoalpha-pyrene, which is a very powerful carcinogenic, and all the enzymatic products are not mutagenic for these cells. That's been one step of enzymatic transformation was able to reduce the environmental impact of these compounds. Also, there is a thermodynamic limitation. No, peroxidases are not able to oxidize all the pHs. Some of the pHs have a high ionization potential, and the redox of the active side of the enzyme is not able to take out 1 electron. Ionization potential, I remind you, is the energy necessary to take out from the molecule 1 electron. But this could be manipulated by site-specific mutagenesis in the enzymes. I will show you some results later. Well, in order to have a good activity on hydrophobic compounds, it's necessary to put the enzyme also in a hydrophobic system. In order to do that, we have covered this cytochrome C, we have covered with polyethylene glycol. It's an amphipathic polymer. And this biocatalyst is fully soluble in organic solvents. It's soluble in dichloromethane, it's soluble in diesel fuel, it's soluble in gasoline, it's soluble in oil. Soluble and active. And here in this table I show you, this is a list of aromatic compounds which are present in petroleum. The cytochrome C unmodified was able to transform only 8 of the list. But this cytochrome, well, something I forget to say, this cytochrome C has been modified chemically on the surface in order to make it soluble. And also we have modified the active site using methyl esterification. We we mask all the carboxylic groups in the active site in order to improve the affinity of the hydrophobic substrate to the active site. And this is a double modification. It's a methylation in the active site and pegylation on the surface. As you can see, the range of the substrate has been increased, and also the activity has been improved, both of them. Why cytochrome C becomes so active? Well, this is a UV spectrum and an EPR, in which we can see that the double modification has disrupted the three-dimensional structure of the cytochrome C in order to lose a 6 coordination. The difference between peroxidase and cytochrome C is the iron in peroxidases is pentacoordinated, and in cytochrome C is hexacoordinated. When we have modified the cytochrome C, the structure has been disrupted, and we got a pentacoordinated iron in the porphyrin ring. And also we got high spin species. That means we have converted a little bit cytochrome C, which is not an enzyme, it's a redox protein. We have converted like a peroxidase. It's for this reason.
If I understand, you replace the
No, the methane is the 6 coordination has been lost. This coordination has been lost. The histidine remain in the proximal side of the. That's right. The coordination, and in this way, the hydrogen peroxide molecule can get easily in the iron, because in order to have, I can go back. Yeah, just to be sure. We haven't substituted. It's just a disruption of the three-dimensional structure. We have changes, and the methionine becomes far from the. We only make chemical modification on the surface, and methylation in the propionates of the heme group. That's right. We are sure even it's possible to see in a circular dichroism the change of the structure. But yes, this the hydrogen peroxide should get here in order to activate. Oof. I'm sorry, at the beginning. We have done also molecular work. I will show you some results. Do you want I repeat all? No. We are close. Okay. This is the reason. This is work with from Franz Arnold, probably you know. He's a very well-known scientist. And they do a very smart transformation in order to do the direct evolution of the it's a bacterial cytochrome P450 for the oxidation of pHs. And they do a E. coli cell in which was cloned the cytochrome P450 and also the horseradish peroxidase in order to see the products of the transformation, the screening system. And they got fluorescence polymers, and in this way they were able to screen hundreds of thousands of different mutants. Well, the important is the results. Here in white, the white bar is the white type cytochrome P450, and after direct evolution, they got, well, this triple variant and in blue bars. I would like to point out the scale of this is logarithmic. That means the increase in activity from the wild type to the triplet mutant is probably 4 or 5 orders of magnitude. this is how powerful is direct evolution. The problem is to have the right screening system. But it's possible to evolve proteins to increase the activity. Well, we arrived to asphaltene. Asphaltenes is a very complex structure. In fact, this is a very old proposition of a structure. Now we know that it's not as big like this, but have several heterocyclic and also aromatic clusters, and these are the petroporphyrines that is present in the asphaltene molecule. Asphaltene are defined only by solubility on pentane. All the components that are not soluble in pentane are considered asphaltene. It's a very complex we know that the molecular weight goes from 500 to 1,000 Daltons. They have a strong tendency to aggregate. It's for this reason we got, in some techniques, we got molecular weights until, I don't know, 50,000 Daltons. And it's the most recalcitrant material of petroleum. In fact, there are not clear evidence that the microorganisms are able to transform asphaltene. And it's important because more of 70 countries have a huge amount of energy on the form of asphaltene. In Canada, it's estimated that the energy in the tar sands in Canada is the amount of energy is larger than the Saudi Arabia as in oil. It's a huge amount of energy that is not used. Only 20% of the energy in the bituminous deposit in Canada are used. This is the facilities in Canada is huge. I don't know if some of you have visited these are huge machines, you know, and it's a bituminous deposit. And I told you only 20% of the energy content is harvested. Well, almost 20 years ago, we were the first to prove that it's possible to get enzymatic oxidation of asphaltene. The key question was to put in the same phase the enzyme and the asphaltene. Asphaltene is highly hydrophobic. It's absolutely not soluble in water. And the problem is not the lack of enzymes able to do. The problem is asphaltene and microbial activity are in different phase. If we put in the same phase using a microemulsion or a ternary system, we were able to transform asphaltene. Here is a petroporphyrin-rich fraction of asphaltene, and is, this fraction treated with chloroperoxidase and very low amount of hydrogen peroxide, the petroporphyrins are destroyed. This is the solid band, which is specific for the porphyrin molecules, and you can see disappear completely. Well, what happened? Petroporphyrins contains nickel and vanadium. These two metals are a problem for the petroleum industry, and we were able to remove significant amount of nickel and vanadium in different. And we have used also our semi-synthetic biocatalyst. This double modified cytochrome C, and this biocatalyst was also able to destroy the petroporphyrin, also using a ternary system. And the removal was higher than with chloroperoxidase, as you can see. With after treatment with cytochrome C, 95% of the vanadium was removed for the asphaltene fraction and 74% of nickel. And the transformation, well, this is just a IR spectra. in which you can see that there is really a transformation of the asphaltene molecule. There are introduction of oxygen atom, carboxylic groups, and hydroxylic, and also the sulfoxide and sulfone are also introduced. This spectrum shows that there is not only the petroporphyrin destruction, but also there is a transformation of the asphaltene. This is a NMR, and you can see some difference. This is important because the reduction of the CH2-CH3 ratio means cracking. And we were very excited about that, because we were able to make an asphaltene molecule cracking by an enzymatic process. This is also I will not take a long time here. It's a difference. And this is the GPC profile, because we were looking if there was a real cracking of the asphaltene. Here is before the enzymatic treatment, and you can see here is the petroporphyrin fraction of the asphaltene, which disappear after treatment. And unfortunately, during the profile, we got that the enzymatic transformer asphaltene showed be a higher molecular weight. There is not cracking, but it's necessary to take these results very carefully, because if you are introducing polar compounds, the asphaltene molecule tends to aggregate more. And probably here is not a problem of size, it's a problem of aggregation. And we are still working on that. Well, this is a BP, this is a result from the BP UNAM collaborative agreement. And we have covered this, the chloroperoxidase. We have covered chloroperoxidase. This is chloroperoxidase with a chitosan in order to have an hydrophilic environment for the protein. And then we have covered with this chitosan and another layer with polyethylene glycol in order to make these particles soluble in organic solvent. And these are some results. You can see these composites or bioconjugates, as you want, are able to transform asphaltene, as you can see by the reduction of the Soret band. And the activity in the chitosan conjugate is higher than the free chloroperoxidase. And the pegylate and chitosan conjugate is more or less the same. Well, this is the kinetic constant of the chitosan bioconjugate in two different systems. And here I would like just to point out that the chitosan's chloroperoxidase conjugate is 4 times more active than the free enzyme in a system with very, very low water content. It's only 6.3% in volume of water. Well, this is also a very interesting result. Asphaltene, because it's a very complex molecule or fraction, there are not many techniques, analytical techniques, in order to find the changes in the asphaltene. We find that if we do an emission excitation matrix using fluorescence technique, we were able to measure aromaticity, more or less. And I would like just to show you 2 results. This is a crude oil, a heavy crude oil from the south of Mexico, in which the aromaticity has been reduced 40%. And this is from Canada, in which the aromaticity has been reduced 36%. That means there is a significant transformation using enzymes of this asphaltene. Well, conclusions. Biodesulfurization is possible to do, using enzymes, chloroperoxidase. Aromatic content reduction also is a potential use from enzymes, and asphaltene transformation is possible. But what are the challenges in order to scale up these processes? Well, first, we need to have activity and stability at a higher temperature, 80. We know that this is possible. It's not really hard. We need to have a catalytic activity in non-aqueous media. And we, in the case of peroxidases, we need to stabilize peroxidases in order to make it more economically attractive. Well, all the peroxidases are inactivated in the presence of hydrogen peroxide. As you can see, some of them are very unstable. That's versatile peroxidase, lignin peroxidase. This is the half-time in 1 millimolar of hydrogen peroxide. Chloroperoxidase is a little more, but it still is inactivated by the presence of hydrogen peroxide. And we have used cytochrome C as model of peroxidases, and we did it a rational engineering of the protein in order to stabilize against the presence of peroxide. Well, this is what happened with peroxidases. You have the destruction of the heme, which is the active site, and also you have changes in the amino acid composition. Obviously, the amino acid residue with low redox potential are oxidized, such as cysteine, methionine, and tyrosine. Sorry. Well, and the inactivation constant increase when the hydrogen peroxide concentration increased. That means more hydrogen peroxide, more unstable is the enzyme. Well, this is the chemical engineer approach or point of view, this cartoon. Well, we have the final electron acceptor, which is the hydrogen peroxide, and we have productive electron flow from the substrate passing through the compound 1 or through the compound 2 to the hydrogen peroxide. However, during the turn-up of the protein, the active site is able to take out electrons from the heme to destroy the heme and to inactivate the enzyme, and also to take electrons from any amino acid residue around the active site and to be inactivated. And the approach was, we would like to improve the flow in this productive electron flow and reduce the non-productive or the inactivating flow. How to do that? Well, we say, if we change the amino acid residue involved in this flow for an amino acid residue with higher redox potential, we will reduce this flow. We can also do the same. In order to manipulate this flow by changing the redox potential of the amino acid residues involved in the electron transfer. If this is true, when we have a low redox potential or low ionization potential substrate, the inactivation was take longer because the flow here will be faster, higher than here. If we increase the ionization potential of this substrate, the inactivation become faster. Yeah? Well, we tested that, and we have used different substrate with different ionization potential. As you can see, this is the logarithm of total turnover number. And when the ionization potential of the substrate is low, the enzyme remain working more time. Wow. The first we did it was eliminated all the tyrosines of the cytochrome C. As shown you in the aminogram, tyrosine disappears. That means tyrosine becomes oxidized during the inactivation process. And these tyrosines are involved in the dimerization of the cytochrome C in the presence of the hydrogen peroxide. And well, this is the electrophoresis of the, this is the native, the wild type cytochrome before and after the incubation in hydrogen peroxide. You can see dimers, trimers, and tetramers. And this is the tyrosine minus variant in the presence of hydrogen peroxide. There is no more dimers and trimers. We eliminated the dimerization with this. Okay, but we will compare the kinetic constants. And unfortunately, you can see the catalytic stability has been reduced 1 order of magnitude. And the activity remains more or less the same. And thinking, well, we say, okay, tyrosine oxidation is not an inactivating event. And we are taking this source of electrons. That means if we take out this source of electrons, the active site will take electrons from the inactivation sources. And we can see clearly here. In fact, it was a wrong strategy. Well, from a collection of variants, we got 2 interesting variants. The first one was a variant which was more stable in the presence of hydrogen peroxide. And other variant which was less sensitive to the increased concentration of hydrogen peroxide. And we have combined both, and we got, this is the double variant in which the heme has been not destroyed. We have stopped the heme destruction, just making these 2 mutations. And making EPR in a very low temperature, we were able to see that the wild type cytochrome C form a free radical in an amino acid based free radical. And the double mutant was unable to form this. We have stopped the formation of an important free radical which is involved in the heme destruction. These 2 mutations are forming with a water molecule a hydrogen bonding network. And we have disrupted this hydrogen bonding network. And without this network, there is no electron transfer to the heme group. We have stopped. What happened with the catalytic constants of still is less active. Well, the heme is stable, we saw, but still there is an inactivation. That means the cytochrome C could be inactivated by heme destruction or by an amino acid residue oxidation that we don't know. And also here, it's not clear, but the activity is very, very low. Well, another low redox amino acid is the methionine 80. Here is the 6 coordination. Well, we take out the methionine and we put alanine, which is higher. And we got a recovery on the activity, but the activity is still low. It's 10 times low. The stability of the heme is higher than in the wild type cytochrome. Another residue around the active site, which is a low redox potential, is the tryptophan 59, and we also take out this one. As you can see, we recover the stability of the heme, but the stability of the enzyme has been reduced again. But we recovered the activity. Still, we have work to do. Finally, this is a phenylalanine which is placed in parallel of the porphyrin and forming a p electron flow. And we have decided also to remove this phenylalanine, and voila, now we have a variant which is one order of magnitude more stable than the wild type, and is preserving the activity. Finally, we have opened the active side, and we got a stable cytochrome C, fully stable in catalytic concentration of hydrogen peroxide, and with the same activity than the wild type. This shows us that it's possible, using a rational approach, to stabilize peroxidases. And to finish, I would like just to show you this Mr. Beckman in 1926 say this. That's mean petroleum biotechnology seems not to be really new. Thank you. Yep.
So you mentioned two challenges in the quote-unquote petroleum age,
Mm-hmm.
labor, energy, and environment. And it seems like you're addressing the energy issue, whereas the environmental issue I don't really see so much. And
Yes, I forget to.
how do you
Mm-hmm.
apply your technology to alleviate the problem?
Yes, I forget you mentioned that in my laboratory we have two main activity fields. One is petroleum biotechnology, and the other one is environmental biotechnology. We do a lot of work in biotransformation of pollutants, pesticides, even aromatic hydrocarbons too. We do. And now here is important. Well, in order to have clean fuels, it's necessary to remove sulfur and to remove aromatic hydrocarbons.
What about CO2?
Pardon me?
What about CO2? So CO2 is inherently in the
Yes, well, but oil is not only energy. No? Look around, you will see oil, and I hope in the next future, oil will be no use to burn, and you need to refine it to use for raw material for anything. Yep.
I had a couple of questions about the pegylated enzyme.
Yep.
So first off, what was the conjugation strategy that you used?
Yeah. We mainly use carbodiamide chemistry to bond free amino groups with carboxylic or whatever. Mm-hmm.
And then the other, oftentimes when you're using pegylated proteins for pharmaceutical applications, you find that the stability is increased.
Yep.
Do you find that also here?
Yeah, we in a pegylate cytochrome C, we are able to have enzymatic activity at 120 degrees Celsius. Yeah, I didn't show, but it's more stable in terms of thermostability. Yeah.
So are these higher PEs or higher molecular weight PEs or
Pardon me?
the PEs, the pegylated which you use? So are these high molecular weight?
The pegylation, oh, we can use wherever. You know, there are a large variety. Usually we use 5,000 kilodaltons pegylation. I remind you, cytochrome C is 12,000 molecular weight. It's very small. And we are able to put 17 polyethylene glycol moieties in the nucleus. At the end, we have a biocatalyst, which is 80% polyethylene glycol and 20% protein.
Is there water associated with that peg layer?
Yeah, well, polyethylene glycol is amphipathic and is able to bind 2 water molecules per ethylene glycol unit. Is for this reason maintain the enzyme in a hydrophilic environment. Enzymes need to have this hydrophilic environment to work. Yeah. In the case of the ternary systems, yes, sure. Yes, it's a microemulsion. It's a microemulsion in which the particle size is smaller than the amplitude of the wave of light wave, and it's clear. It's translucent, but it's an emulsion.
If there aren't any other questions, I'd like to thank Professor Vazquez-Duhalt.
Okay.